Data augmentation is a pretty powerful tool to boost the performance of your code. Today I want to show you a simple example with linked lists. Let's analyze this sample code that I've prepared. Here in my main I have a pointer to a node, which is the head of my linked list with the value null. A node is essentially this struct which contains data and a pointer, of course, to the successive node of the list. Then I have an infinite loop in which I will call the function append time, passing as an input the address of my head and a random value, let's say 42. So the function append time basically is calculating the time that it takes to append a node inside my linked list. To do that, I use the clock getTime function and a struct timeSpatch, which is just the struct that contains seconds and nanoseconds. The append function is creating a new node and initializing to value and null, and then it appends. If the head is null, so if my linked list is empty, I just append a node to the head. Easy. And return. On the contrary, you have to loop to search the last node of the list. And this is where the bottleneck is, because if the list is long, this will take more and more time. And then you simply append the node. And running the code, we see that every successive append takes more and more time, right? And this makes sense because the list is becoming bigger and bigger. The bottleneck is here because the loop takes time to reach the final node. So we can do much better than this. As you can see, we are reaching almost the millisecond average to append a node in a linked list with this many elements. So if you have to work with big lists, you need something better. We can do data augmentation in this case. So I change a little the code, I just add this node to tail, okay? Then the code is exactly the same, just my append function takes also a pointer to this tail. So I have my node creation, but this time I check. If the list is empty, what do? You append the node and you also update the tail to point to the new node in this case. On the contrary, and this is where you get constant access time, here you append the node in the linked list accessing the next field of the tail node. And you append in this fashion, constant time. And then you simply update the tail, right, which now is the new node. So this is much better, much cheaper than looping all the nodes inside your linked list. If I run this code, you can see that appending a node takes constant time. It's basically free. You get appending for free just having a pointer to the last element of the linked list. So this is a pretty remarkable improvement performance-wise, and it's almost necessary if you need to deal with big linked lists. So I have this final piece of code in which I want to see the performance improvement of using a linked list with a tail or not. So here I have my list with a tail, which is a struct with a pointer to the head and a tail. And I have the append, which is basically using a boolean, use tail or don't use tail, which I have the append using the tail or the append using the loop. No, nothing really fancy. So here you can see the full code. You can stop the video if you want to check more details, but nothing really fancy. I just want to run this, and as we see, if the list is very little, I don't have any reasonable improvement. But as the list is becoming bigger and bigger, I start to have bigger and bigger improvements. As you can see, when I have 256, I have a 5x improvement. 512 nodes, 6x improvement. 1000 nodes, I get a 15x improvement, which is already a very big improvement. The bigger the list, the bigger the improvement. For 8000 nodes, I get an 100x improvements in performance. That's crazy, right? That's a lot. And if I have 65,000 nodes, I get a 800x improvement. So as you can see, with a simple piece of code, you can get a remarkable improvement in your code performance.